Today we will solve a dynamics problem using planar kinetic equations of motion. So let's analyze the problem. Here we can see a man is pushing at the table this direction F, which is creating 30-degree angle. The dimension of the table is given, and the total weight of the desk is given, which is 75 pounds, which should be acting at the Z point here. So the given is weight 75 pounds, and we have to find the initial acceleration when F, the force the man is applying on the table, is just overcome the static friction. And the problem also asks to find the normal reaction at point A and B of two legs. So each A here has two legs, one is here and one we cannot see, and then also so table has four legs, so two legs each of those we have to find. Before we start solving problem or discuss what would be our first thought is, let me take a moment to clarify or simplify the things about statics and dynamics. It'll be easier for understanding the planar kinetic equations of motion. So if you remember your statics, all we had to do is the summation of all forces was 0. So summation of forces in x direction or y direction would be equals to 0. And if we take any moments about any point P for statics, we would also put the summation of all moment equals to 0, and we would solve for our variables. In dynamics, the easiest way to remember is that you will have the same equation, summation of all force, since dynamics is in motion and we need unbalanced force. So unbalanced force causes the motion, and instead of 0 we will have MAG. So acceleration about point Z here, the center, mass center Z. And also the moment about any point P on the body. It could be A, it could be Z, or point D here. The moment about any point would be, instead of equals to 0 in statics, in dynamics we will have it will be equals to MK, kinetic moment about the same point P. Now let's look at the kinetic moment MK. It can have three terms. If we know the acceleration of the desk, the x component is AXG because Z is the mass center, and then y component of the acceleration is AYZ. So we can have, F equals to ma, force equals to mass into acceleration. So this part MAX would be your force, and y prime would be the distance. So it's still a moment. That's why we call it kinetic moment, because ma is the acceleration part involved. This is here also MAY part. This is the again force part, and x is the distance, so it's a moment. And we also have the angular acceleration part. Since this problem is the table is not rotating, so this becomes 0, and then we have to decide whether we have acceleration in y direction, which is not, because this is moving only on this direction. So we will have AY 0, so we will not have this term and this term. So for the moment, for kinetic moment, we will have only this term available to use. But again, we're going to come to this part when we solve the problem. So now let's start solving our problem. So our first thought reading the problem is that it's a general plane motion, GPM, and it's translation, so it's not rotating, the desk is not rotating. And the question asks to find acceleration when the force applied by the man is only causing to overcome the static friction. So maybe we have to start with the static part of the problem, and then maybe we'll move to dynamics part. And for dynamics, to connect with force, we to find the acceleration ma, we need to find the force. So maybe we have to find the force first, and then so that we can connect and find A. And for the normal reaction at point A and B, we can take moment about any point to find A and B. So these are for understanding, since our static coefficients of static friction is given, coefficient of kinetic friction is given. So maybe we can use the coefficient of kinetic friction, coefficient of static friction, to find the minimum force that requires to overcome the static force, and then maybe we'll use that force to find the dynamics part. So let's start solving problem. So according to our plan, our first goal is to use statics and find the force F the man will be applying to just overcome the static friction. So we're taking statics under consideration. So summation of force in x direction is equals to 0. The forces are acting the x component of F, so which is F cos theta, and all the reaction of that force is the friction against the direction of force, so it will be negative. And since we are talking about statics, so I have to use the static coefficient of friction, and this is for the NA and NB. So NA represents the normal force of 2 legs at A, and NB represents the reaction at 2 legs at point B. So this is our first equation, and if we take the y component, so summation of y equals to 0, we can again have the normal reaction at all those 4 legs of the desk, so NA plus NB, and now we have the negative component of the force, right? So F is acting this direction, so it has an x component and y component, so this is negative, it is downwards, so negative sine 30, and we also have the weight of the table, 75 pounds, so we put it negative downward. So from this equation we can find, if I take this 2 part on the other side, we get NA plus NB equals to this. If we plug this NA plus NB value up here, we can solve for force B. So the value of force will be 60.874. One question you ask during the class is that once we find the force F equals to 60.874, can we plug back this force here and here to solve for NA plus NB? Well, what is the problem is that if you try yourself, plug this F value here and here, both equations, so this equation 1 and 2, both become identical. So there will be only one equation it will form. And since we will have 2 unknowns, NA and NB, we cannot solve the problem because we have 2 unknowns and one equation. So what we have to do, we have to proceed further to the dynamics part of the problem, and maybe we'll solve from there. So in our dynamics part, we will start with the simplest equation we have. Since it's a translation, so we'll start with our translation equation. Summation of force in x direction would be equals to mass into acceleration in x direction, which will be F cos 30 degree, the x component, and then 0.2. This is the dynamic coefficient of friction, not the static, because now we're on the dynamics part. This is the change. In previous equation we used 0.5, which was the static part. Now we're gonna using the dynamic part. Now we know the value of F that we figured out in previous slide, 60.87 pound. We know cos 30. We also for static part we know NA plus NB. We found it 75 plus F sine 30 degree. And we know the mass because the weight is given 75 pounds. We have to divide it by 32.2. So only unknown will be AX Z in this equation. So if we solve for that, we will get 13.58 feet per second squared. This is the acceleration according along x direction, since we don't have a y acceleration in y direction of point z, so that will be 0. So if we take y component and x component, we will have the total acceleration according to ax square plus ay square, and since ay is 0, our total acceleration would be the same value as axc, which is 13.58 feet per second square. So we have found our acceleration, but we still need to find NA and B. So our next step would be hunting for reaction NA and NB, and for that what are we gonna do is that we're gonna use the moment equation for the planar kinetic equations. So we can take moment about point A or point B or point Z, but we have to think which point would be easier, since the force F has x component and y component. So if we take moment about point A, so then we can cancel out two forces, normal NA and also the Fy component. So for now, let's take the moment about point A. That will reduce two variables, so it may be useful. You can always take for moment for point B and Z. Those will also lead you solution, but it may take longer. So now let's take moment about point A here. We have the Fx component, so Fx costs 30 and multiplied by the distance 2 plus 1, so 3, and it's acting this direction. So the force Fx is creating a moment about this direction, which is clockwise, so we put negative. We also have the weight acting this direction, so if I take moment about this point, so it's also gonna to make a clockwise moment, so it's again negative, multiplied by distance here to here, which is 2, and all we have left is that the force NB, normal force here, and we're taking moment about this point, so the distance is this 2 plus 2 4, and it's creating upwards, so it is creating counterclockwise, so we put it positive NB. On the right side, the kinetic moments is our mass into acceleration in x direction, which is the total ma, which is sense of force, multiplied by the y bar, which is y bar, so point A to point Z height, which is 2. So mass, we know we can get it from the weight. Acceleration, we just found it in previous slide. Y bar is 2, so only unknown will be NB. Weight is again 75, we know, F we already found. So if we plug all those values, we can get the NB 61.2 pound. Remember at the beginning we told you that the NB is of the two legs. So NB actually representing the two legs on the B side. So for one leg, we can say for one leg the reaction would be, for one leg, it will be half of 61.2, which would give you 30.6 pound. Now remember, we also had from the statics part that NA plus NB equals to 75 minus F sine 30 degrees. So if we plug this NB value down here, we can get the NA, which is 70, the reaction at two legs at point A. So this leg we can see, and the other leg that we cannot see, parallel to A, which is 42.2. So for one leg, it will be half of 44.2, which would be NA prime. If we take the half, it will be 22.1 pound. So our reaction on each leg is 22.1, and then a reaction at each leg at point B is 30.6. But if we're in general, if we are looking for only the reaction at A or B, our answer would have been for NB 61.2, and then for NA 44.2 pounds. But when we're looking for each leg, so we have to divide it by 2 to get NB and NA prime, which is 22.1 pound. So these are the answers. If you have any question, you can always comment, and then I can explain you more. See you in next class.